Objects from other star systems are crashing through our cosmic neighborhood right now. You can't see them coming. Most people assume space between stars stays empty forever. That assumption just got shattered by wanderers moving faster than bullets. Tonight we're discovering why these cosmic refugees are revolutionizing astronomy, and how they're revealing secrets from alien worlds we'll never visit. Before we dive into these space nomads, drop a comment about where you're listening from. If you enjoy these cosmic mysteries, consider subscribing. These explorations are meant to be shared across the universe. Hawaiian telescopes caught something unprecedented in October 2017, a faint dot racing across space. At first glance, this seemed ordinary. Within hours, astronomers realized they were witnessing history. The object's path through our solar system proved it came from somewhere else entirely. Here's how we know this visitor wasn't born here. Every object in our solar system follows a curved path around the sun. Think of planets orbiting in circles or ovals. They're trapped by the sun's gravity forever. But this wanderer followed a completely different type of path. An open curve that swoops in once and escapes forever. Scientists call this a hyperbolic trajectory. It's like the difference between a car going around a traffic circle versus a car that cuts straight through and drives away. Oumuamua was moving at 26 kilometers per second relative to our sun. That extra speed beyond what our sun's gravity could provide proved this object had been traveling between the stars. For the first time in human history, we were observing a messenger from another star system. Between star systems lies an ocean of almost perfect emptiness. Oumuamua had been crossing this void for an unimaginable amount of time before discovering our solar system. This space between stars contains almost nothing. No air, no obstacles, just scattered atoms and microscopic dust particles floating in the darkness. It's emptier than any vacuum we can create on Earth. Objects traveling through this emptiness encounter almost no resistance. They maintain their speed and direction with mechanical precision, like a hockey puck sliding across perfectly smooth ice that stretches for trillions of miles. Oumuamua approached from the direction of a constellation called Lyra. Its velocity perfectly matched what we'd expect from an object drifting through our local galactic neighborhood. When our solar system's gravity grabbed this wanderer, it transformed from cosmic drifter into temporary visitor. Our sun bent its path, accelerated it to incredible speeds, then released it back into the galactic wilderness forever. Oumuamua looked like nothing we'd ever seen in our solar system. Most asteroids and comets are roughly round or potato-shaped. This visitor was stretched out like a cosmic cigar. Scientists measured its dimensions by watching how its brightness changed as it tumbled through space. The object was roughly 10 times longer than it was wide. Imagine a skyscraper lying on its side, spinning end over end. No natural process in our solar system creates objects this elongated. Our asteroids and comets get pounded into roughly spherical shapes by billions of years of collisions. They break apart and reform until they reach more balanced proportions. This extreme shape suggested Oumuamua formed under very different conditions than anything in our cosmic neighborhood. Either it came from a place where collisions happen differently, or it was created by some process we don't understand. The visitor's bizarre geometry became our first clue that objects from other star systems might be fundamentally different from our cosmic neighbors. Oumuamua wasn't just spinning, it was tumbling chaotically through space. Astronomers discovered this by measuring how the object's brightness changed over time. As the elongated visitor rotated, different amounts of its surface reflected sunlight toward Earth. When the long side faced us, it appeared brighter. When the narrow end pointed our way, it dimmed dramatically. The brightness changed by a factor of 10. But the pattern wasn't regular like a simple spinning top. The brightness variations followed a complex, unpredictable rhythm. This told scientists the object was tumbling in multiple directions simultaneously. This chaotic rotation suggested a violent past. Something had knocked Oumuamua off its original spin axis. Perhaps a collision in its home star system, or maybe gravitational forces from passing stars had gradually twisted its rotation over millions of years of interstellar travel. The tumbling motion preserved the memory of cosmic violence from long ago and far away. Oumuamua moved through our solar system faster than astronomers had ever tracked an object before. Within months of its closest approach to the Sun, the visitor had already begun its journey back to interstellar space. The object's tremendous speed meant scientists had only a brief window to study it. Every day that passed, Oumuamua grew fainter and harder to observe. Telescopes around the world raced to gather data before losing sight of the visitor forever. Most comets and asteroids hang around our solar system for years or even decades. They follow predictable paths that give scientists plenty of time to plan observations. But Oumuamua was just passing through on a one-time visit. By the time astronomers fully realized what they were looking at, the cosmic wanderer was already speeding away from the Sun. This rapid passage taught scientists they needed faster response systems to study future interstellar visitors. The next cosmic messenger might move through our neighborhood just as quickly. Oumuamua earned a unique place in scientific history. This small wanderer became the first confirmed interstellar object ever detected by humanity. For decades, astronomers had theorized that objects must occasionally drift between star systems. Computer models predicted we should see roughly one interstellar visitor per year passing through our cosmic neighborhood. But theory and reality are different things. Scientists had been looking for these cosmic wanderers for years without success. Every moving object they found turned out to belong to our solar system. Asteroids, comets, and space debris all followed the gravitational rules of our Sun's influence. Oumuamua changed everything by providing proof that the galaxy contains pneumatic objects traveling between stars. This discovery opened an entirely new field of astronomy. Scientists realized they needed better detection systems to catch future visitors. The cosmic wanderer showed us that our solar system exists within a vast network of drifting objects that connect star systems across the galaxy. Oumuamua was discovered purely by accident. Hawaiian telescopes weren't looking for interstellar visitors when they spotted the faint moving dot in October 2017. The Pan-STARRS telescope system was designed to hunt for potentially dangerous asteroids that might threaten Earth. Every night, these robotic eyes scan the sky for moving objects that could pose collision risks to our planet. On October 19th, automated software flagged an unusual detection. A faint point of light was moving across the sky faster than typical asteroids. At first, astronomers assumed they'd found another piece of space debris from our solar system. But when they calculated the object's orbit, the numbers didn't make sense. The trajectory suggested something impossible. An object that wasn't gravitationally bound to our Sun. It took days of additional observations to confirm what seemed unbelievable. This cosmic wanderer had arrived from somewhere else entirely. The accidental discovery revolutionized our understanding of what travels through the space between stars. Scientists couldn't agree on what to call Oumuamua or how to classify it. The object broke every existing category for solar system residents. Initially, astronomers labeled it as Comet C 2017 U1. This designation suggested a typical icy visitor that would develop a glowing tail as it approached the Sun. But Oumuamua showed no signs of the gas and dust emissions that define comets. Then they reclassified it as Asteroid 2017 U1. But asteroids are supposed to be rocky debris left over from planet formation in our solar system. This visitor clearly came from somewhere else entirely. Finally, scientists created an entirely new category. They redesignated the object as 1I 2017 U1, the I standing for Interstellar. The name Oumuamua comes from Hawaiian and means scout or messenger from afar arriving first. This naming confusion revealed how unprepared the scientific community was for interstellar visitors. Our classification systems assumed everything we detected would belong to our solar system. Oumuamua forced astronomers to create new categories for cosmic wanderers from other star systems. By the time astronomers realized what Oumuamua truly was, the cosmic visitor was already racing away from Earth. The scientific community had missed its best chance to study humanity's first confirmed interstellar messenger. The object was discovered when it was already past its closest approach to the Sun and heading back toward deep space. Every day that passed, Oumuamua grew fainter and more difficult to observe with telescopes. Scientists scrambled to gather data from the fading visitor. Research teams around the world requested emergency observation time on major telescopes. But most detailed studies require weeks or months of preparation. The cosmic wanderer wouldn't wait. Within a few months, Oumuamua had faded beyond the detection limits of even the largest ground-based telescopes. The brief observation window taught astronomers a crucial lesson about cosmic timing. Future interstellar visitors might move through our neighborhood just as quickly. The scientific community needed faster response systems and better coordination to study the next cosmic messenger before it disappears back into the galactic void. Oumuamua did something that should have been impossible. As it moved away from the Sun, the object accelerated slightly beyond what gravity alone could explain. Scientists noticed this anomaly when they tried to predict the visitor's future path through space. Their calculations, based purely on gravitational forces, didn't match the object's observed trajectory. Something was giving Oumuamua an extra push. This mysterious acceleration was tiny but definitely real. The effect was roughly equivalent to the gentle pressure of sunlight hitting the object's surface. But Oumuamua showed no signs of the gas emissions that typically cause non-gravitational aeration in comets. The unexplained motion transformed a simple discovery into one of astronomy's most puzzling mysteries. Scientists proposed various theories: hidden gas emissions, unusual surface properties, or even more exotic explanations. But without more detailed observations, the true cause of Oumuamua's mysterious acceleration remains unknown. This cosmic visitor left our solar system carrying its secrets back to the depths of interstellar space. Oumuamua's discovery revolutionized our understanding of what exists in the space between stars. This single cosmic wanderer proved that our solar system sits within a vast network of drifting objects. The implications extend far beyond one strange visitor. If interstellar objects pass through our cosmic neighborhood regularly, they represent natural probes from other planetary systems. Each wanderer carries information about conditions around distant stars. Scientists realized these cosmic messengers could teach us about planet formation in other star systems. They might reveal whether the processes that built our solar system are typical or unusual among the galaxy's stellar families. The discovery also suggested that material regularly moves between star systems, over billions of years. This cosmic exchange might have distributed organic molecules or even primitive life forms across the galaxy. Oumuamua opened our eyes to the possibility that our solar system isn't an isolated island, but part of a connected galactic community. The cosmic wanderer showed us that the space between stars isn't empty. It's filled with travelers carrying stories from distant worlds. Every night, robotic telescopes scan the Hawaiian skies hunting for dangerous asteroids. These automated systems work tirelessly while astronomers sleep. They're designed to protect Earth by spotting space rocks that might threaten our planet. On October 19, 2017, the Pan-STARRS telescope detected a moving point of light. The computer flagged it as just another routine discovery. Software algorithms automatically tagged it for follow-up observations. Pan-STARRS stands for Panoramic Survey Telescope and Rapid Response System. This robotic observatory photographs the same patches of sky repeatedly. By comparing images taken hours apart, computers can spot anything that moves against the background of distant stars. The detection itself seemed completely ordinary. A faint dot shifting position between photographs. The automated system had no idea it had just captured something unprecedented. This routine scan accidentally became the first confirmed detection of an object from another star system. Sometimes the most revolutionary discoveries happen when we're looking for something else entirely. When astronomers first calculated the visitor's orbit, the numbers made no sense. Every object in our solar system follows predictable mathematical rules, but this wanderer's path broke those rules completely. Scientists use orbital mechanics to predict where space objects will travel. These calculations work perfectly for everything born in our solar system. Planets, asteroids, and comets all follow paths that mathematical formulas can describe precisely. But Oumuamua's trajectory defied these standard equations. The visitor's path suggested it had more energy than our sun's gravity could provide. It was moving too fast to be a native resident of our cosmic neighborhood. At first, astronomers assumed they'd made calculation errors. They double-checked their math repeatedly. Different research teams ran independent calculations using the same observational data. Every analysis reached the same impossible conclusion. This small object possessed excess velocity that could only come from interstellar space. The mathematical impossibility forced scientists to accept they were witnessing something that had never been confirmed before. Could astronomers worldwide mobilize their most expensive equipment for a single fading target? Oumuamua was already speeding away from the sun when scientists realized what they'd found. Every hour that passed made the visitor dimmer and harder to study. Research teams issued emergency requests to major observatories around the globe. These facilities normally require months of advance planning to secure observation time. Scientists had to abandon scheduled projects to focus on the disappearing visitor. The European Southern Observatory pointed its very large telescope at the cosmic wanderer. NASA's Hubble Space Telescope interrupted its regular program to track the fading object. Ground-based observatories in Child, Hawaii, and the Canary Islands joined the international effort. This unprecedented coordination demonstrated how quickly the global astronomy community can respond to extraordinary discoveries. The race against Oumuamua's fading light became a proof of concept for future interstellar visitor studies. When the next cosmic messenger arrives, scientists will know how to mobilize resources before it disappears forever. What do you call something that doesn't fit any existing category? Oumuamua broke every classification system astronomers had developed for solar system objects. Scientists initially labeled the visitor as comet C 2017-U1. The C designation indicates a comet, an icy object that develops a glowing tail when heated by the sun. But Oumuamua showed no signs of the gas and dust emissions that define comets. Next, they reclassified it as asteroid 2017-U1. The A stands for asteroid, rocky debris left over from our solar system's formation. But asteroids belong to our sun's gravitational family. This visitor clearly came from somewhere else. Finally, astronomers created an entirely new classification system. They redesignated the object as 1I 2070-U1, the I representing Interstellar. The classification crisis revealed how unprepared science was for visitors from other star systems. Oumuamua forced the creation of new categories that will be used for all future interstellar objects. Light carries information about whatever reflects it. When astronomers analyzed the sunlight bouncing off Oumuamua, they discovered clues about conditions in alien star systems. Spectroscopy is the science of studying light to understand materials. Different substances absorb and reflect specific colors of light in characteristic patterns. By analyzing these spectral fingerprints, scientists can determine what objects are made of without ever touching them. Oumuamua reflected light with a reddish tint. This coloration suggested the visitor's surface contained organic compounds or had been weathered by cosmic radiation over millions of years of interstellar travel. The red color resembled objects in the outer regions of our own solar system. Bodies like Pluto and some asteroids show similar hues. But Oumuamua's spectrum was subtly different, hinting at formation conditions unlike anything in our cosmic neighborhood. The color analysis provided the first direct evidence about the composition of matter from another star system. Why does Oumuamua's brightness change in a regular pattern? As the cosmic visitor tumbled through space, it reflected different amounts of sunlight toward Earth in a predictable cycle. Astronomers measured these brightness variations to determine the visitor's rotation period. The object completed one full rotation every 7.3 hours. This relatively rapid spin suggested something had knocked Oumuamua off a more stable rotational state. The brightness changed dramatically during each rotation cycle. When the object's long side faced Earth, it appeared much brighter. When the narrow end pointed toward us, the reflected light dimmed significantly. This brightness pattern confirmed the visitor's extremely elongated shape. A spherical object would show little brightness variation as it rotated, but Oumuamua's dramatic dimming and brightening revealed its cigar-like geometry. The rotation period became another piece of evidence that this cosmic wanderer formed under very different conditions than objects in our solar system. How do you measure something millions of miles away? Scientists used Oumuamua's brightness and assumed reflectivity to calculate the visitor's actual dimensions. The calculation required educated guesswork about the object's surface properties. Scientists assumed Oumuamua reflected light about, as well as typical asteroids in our solar system. This assumption allowed them to work backwards from brightness to size. The results suggested a remarkably small cosmic wanderer. Oumuamua measured roughly 200 meters long and 35 meters wide. That's smaller than most city blocks, but stretched out like a cosmic skyscraper lying on its side. This compact size explained why the visitor had remained undetected for so long despite passing relatively close to Earth. Small objects reflect very little sunlight, making them nearly invisible until they approach the inner solar system. The size calculation revealed that countless similar wanderers might be drifting through space undetected. Oumuamua represented the tip of an iceberg of interstellar visitors too small and dim for our current detection systems. Can infrared telescopes detect heat from an object racing away at millions of miles per hour? Scientists attempted to measure Oumuamua's surface temperature using its thermal emission. Every object warmer than absolute zero emits infrared radiation. The amount and wavelength of this heat signature reveals information about surface temperature, composition, and thermal properties. Infrared astronomy allows scientists to study objects that are too dim or distant for visible light observations. But Oumuamua presented unique challenges for thermal measurements. The visitor was small, distant, and moving rapidly away from both the Sun and Earth. Its surface temperature was changing constantly as it traveled farther from our star's warming influence. Despite these difficulties, infrared observations provided valuable data about the visitor's thermal behavior. The measurements suggested Oumuamua's surface properties differed subtly from typical asteroids and comets in our solar system. The thermal signature hunt demonstrated the limits of current technology for studying rapidly departing interstellar visitors. Scientific rivalry transformed into unprecedented cooperation when Oumuamua appeared. Normally competitive research teams shared data freely to maximize what humanity could learn from this cosmic visitor. Major observatories that rarely coordinate their efforts work together seamlessly. The European Southern Observatory, NASA's space telescopes, and ground-based facilities around the world synchronized their observations. This collaboration maximized the scientific return from every precious hour of observation time. Different telescopes contributed specialized capabilities. Some excelled at measuring brightness changes, others captured spectral data. Space-based instruments avoided atmospheric interference. The cooperation extended beyond just sharing telescope time. Research teams openly shared their preliminary results and analysis techniques. This transparency accelerated the pace of discovery and ensured that crucial insights wouldn't be delayed by traditional publication processes. The international collaboration established new standards for studying future interstellar visitors. Time was running out faster than anyone anticipated. Oumuamua was fading from view more rapidly than scientists had calculated. Every observation session might be the last chance to gather data from humanity's first confirmed interstellar visitor. Astronomers pushed their equipment beyond normal operating parameters to squeeze out every photon of reflected light from the departing object. They extended exposure times to their maximum limits. They combined multiple images to increase sensitivity. Ground-based telescopes competed with moonlight, atmospheric interference, and the visitor's rapid motion across the sky. Even the largest observatory mirrors struggled to collect enough light for meaningful measurements as Oumuamua raced toward the outer solar system. By early 2018, the cosmic wanderer had faded beyond the detection limits of all but the most powerful telescopes. The observational deadline forced scientists to prioritize their most important questions and accept that many mysteries about Oumuamua would remain unsolved. The fading race taught astronomers crucial lessons about preparing for future interstellar visitors that might move through our neighborhood just as quickly. Oumuamua accelerated when it should have been slowing down. As the cosmic visitor moved away from the Sun, something gave it an extra push that gravity alone couldn't explain. Scientists noticed this anomaly when they tried to predict the object's future path through space. Their calculations, based purely on gravitational forces, didn't match Oumuamua's observed trajectory. The visitor was moving slightly faster than physics predicted. This mysterious acceleration was incredibly small but definitely real. The extra push was roughly equivalent to the gentle pressure of sunlight hitting a solar panel. But Oumuamua showed none of the gas emissions that typically cause such effects in comets. Non-gravitational acceleration usually comes from material streaming off an object's surface. When comets approach the sun, they heat up and release jets of gas and dust. These emissions act like tiny rocket engines, subtly changing the comet's orbit. But Oumuamua remained completely inactive throughout its passage through our solar system. The mysterious push transformed a straightforward discovery into one of astronomy's most puzzling riddles. Unlike every comet ever observed, Oumuamua remained completely inactive as it approached the sun. No glowing atmosphere formed around the visitor. No brilliant tail stretched behind it through space. Comets are essentially dirty snowballs made of ice and rocky debris. When they venture close to the sun, solar radiation heats their frozen surfaces. Water and other ices transform directly from solid to gas in a process called sublimation. This creates the glowing coma and spectacular tail that make comets famous. Oumuamua experienced the same intense solar heating as any comet passing this close to the sun. The visitor approached within 23 million miles of our star. At that distance, surface temperature should have reached hundreds of degrees. Yet the cosmic wanderer showed no signs of activity whatsoever. No gas emissions, no dust release, no brightening or tail formation. This complete absence of cometary behavior suggested Oumuamua was made of something much more stable than typical comet ices. The quiet passage raised fundamental questions about what materials from other star systems might be composed of. Oumuamua's estimated density created an impossible contradiction. Depending on which measurements scientists trusted, the visitor was either impossibly light or impossibly heavy for its observed behavior. Density calculations require knowing both an object's size and its mass. Scientists estimated Oumuamua's dimensions from its brightness and assumed reflectivity, but determining the visitor's mass proved much more difficult. The mysterious acceleration provided clues about the object's mass. Lighter objects respond more strongly to small forces than heavier ones. Based on how much Oumuamua accelerated, scientists calculated it must be remarkably low density, almost like cosmic foam. But this low density contradicted other observations. An object that light and porous should have shown signs of breaking apart during its close approach to the sun. Tidal forces and thermal stress should have shattered such a fragile visitor. The density puzzle suggested Oumuamua possessed internal properties unlike anything in our solar system. Oumuamua wasn't simply spinning, it was tumbling chaotically in multiple directions simultaneously. This complex rotation pattern provided clues about the visitor's traumatic history. Most objects in space settle into stable rotation around a single axis. Like a spinning top, they maintain consistent orientation as they move through space. This happens naturally over time as small forces gradually smooth out irregular motion. But Oumuamua's rotation defied this natural tendency toward stability. The visitor tumbled in what astronomers call a complex rotation state. Its brightness varied in unpredictable patterns as different surfaces reflected sunlight toward Earth. This chaotic tumbling suggested something violent had disrupted the visitor's original spin. Perhaps a collision in its home star system knocked it off its stable rotation axis, or maybe gravitational encounters with passing stars had gradually twisted its motion over millions of years of interstellar travel. The tumbling motion preserved evidence of cosmic violence from Oumuamua's mysterious past. Light bouncing off Oumuamua carried subtle clues about the visitor's surface materials. The reflected sunlight showed a distinctly reddish tint that told a story of cosmic aging. This red coloration resembles objects in the outer regions of our own solar system. Bodies like Pluto and some distant asteroids show similar hues. The color comes from organic compounds and radiation damage accumulated over vast periods of time. Space radiation acts like cosmic sandpaper, gradually altering surface materials over millions of years. High-energy particles from stars and cosmic rays break down complex molecules and create new compounds. This process, called space weathering, slowly turns originally gray surfaces reddish-brown. Oumuamua's red color suggested the visitor had been wandering through interstellar space for an incredibly long time. The cosmic weathering had slowly transformed its surface composition during eons of travel between the stars. The reddish hue became a cosmic odometer, recording the vast distances and timescales of the visitor's interstellar journey. What holds Oumuamua together? The visitor's extreme elongated shape raised questions about its internal structure that scientists couldn't answer with distant observations. Most objects in our solar system are either solid rocky bodies or loose collections of rubble held together by weak gravity. Geologists call these loose aggregates rubble piles. They're basically cosmic gravel heaps that can barely hold together under their own weak gravitational pull. Oumuamua's cigar-like shape created unique structural challenges. An object 10 times longer than it is wide would experience enormous stress forces during acceleration and rotation. A typical rubble pile would likely break apart under such conditions. Yet the visitor remained intact throughout its passage through our solar system. This suggested either unusually strong internal structure or composition unlike anything familiar to planetary science. The structural mystery highlighted how little we understand about materials and conditions in other star systems. Objects from alien worlds might possess properties that challenge our Earth-based assumptions about how cosmic bodies form and survive. Where did Oumuamua come from, and what processes created such an unusual object? The visitor's bizarre properties provided no clear answers about its formation history. Scientists proposed several possible origins for the cosmic wanderer. Perhaps it formed as debris from a collision between larger bodies in its home star system. Asteroid impacts can create fragments with unusual shapes and compositions. Alternatively, Oumuamua might be a remnant from the tidal disruption of a larger object. When small bodies pass too close to massive planets or stars, gravitational forces can stretch them into elongated shapes before tearing them apart. A third possibility involved entirely different planetary formation processes. Maybe other star systems create objects under conditions that don't exist in our cosmic neighborhood. Different stellar environments might forge materials and structures we've never encountered. The origin enigma reminded scientists how much they still don't know about planetary system formation beyond our own solar system. Could Oumuamua be made of pure hydrogen ice? This exotic possibility might explain the visitor's mysterious acceleration without visible gas emissions. Hydrogen is the most abundant element in the universe. Under extremely cold conditions, it can freeze into solid ice. But hydrogen ice behaves very differently from the water ice that makes up typical comets. When hydrogen ice sublimates, it releases gas that's nearly invisible to most telescopes. Unlike water vapor or dust, hydrogen emissions are incredibly difficult to detect from Earth. A hydrogen iceberg could produce rocket-like thrust while appearing completely inactive to observers. This theory required Oumuamua to have formed in an environment cold enough to freeze hydrogen, temperatures near absolute zero. Such conditions might exist in the outer regions of other star systems or in the frigid depths of interstellar space. The hydrogen iceberg hypothesis offered an elegant explanation for the visitors' puzzling behavior. But proving it would require much more sensitive instruments than were available during Oumuamua's brief visit. What if Oumuamua resembled a chip of Pluto's frozen surface? Scientists proposed that nitrogen ice could explain the visitor's strange properties. Pluto's surface contains vast plains of frozen nitrogen. This exotic ice behaves differently from ordinary water ice. Nitrogen sublimates at much lower temperatures, creating gas emissions that are difficult to detect with Earth-based telescopes. A fragment of nitrogen ice could accelerate without producing visible emissions. As the exotic ice slowly sublimated in sunlight, it would create invisible thrust while maintaining a clean, inactive appearance. This theory suggested Oumuamua might be a piece of an alien world's frozen atmosphere. Many planets and moons beyond our solar system likely have nitrogen-rich surfaces similar to Pluto. Collisions or other processes could knock chunks of these frozen worlds into interstellar space. The nitrogen ice theory provided a testable explanation that connected Oumuamua's behavior to familiar planetary science, even if the specific conditions remained exotic by Earth standards. Could Oumuamua be riding the solar wind like an electric surfer? This unconventional theory proposed that the visitor gained speed through electromagnetic interactions rather than traditional rocket effects. The solar wind consists of charged particles constantly streaming away from the sun. These particles carry electrical energy that can interact with conductive surfaces. Under the right conditions, an object could use this electromagnetic environment to generate thrust. An electric sail would require Oumuamua to possess unusual electrical properties. The visitor's surface would need to accumulate electric charge and interact with the solar wind's magnetic field in ways that create acceleration. This model drew inspiration from proposed spacecraft designs that use electromagnetic effects for propulsion. While no natural objects in our solar system behave like electric sails, conditions in other star systems might create materials with exotic electromagnetic properties. The electric sail concept pushed the boundaries of conventional planetary science into territory that bordered on speculative physics. Was Oumuamua natural, or could it be something else entirely? The visitor's unprecedented properties forced some scientists to consider possibilities that astronomy rarely contemplates. Every characteristic that made Oumuamua unique also made it unlike any natural object ever observed. The extreme elongated shape, the mysterious acceleration, the complete absence of cometary activity, the unusual rotation pattern. Some researchers quietly wondered whether these properties might be engineered rather than natural. Could an artificial object explain behaviors that seemed impossible for cosmic debris? This speculation remained highly controversial within the scientific community. Most astronomers preferred natural explanations, no matter how exotic, over artificial ones. But Oumuamua's combination of unusual properties challenged conventional thinking about what travels through interstellar space. The artificial object debate highlighted how the visitor pushed scientific understanding beyond the boundaries of familiar planetary science. What if Oumuamua was mostly empty space held together by cosmic glue? The dust bunny hypothesis proposed that the visitor consisted of incredibly porous, lightweight material. This model envisioned Oumuamua as an aggregate of tiny particles bound together by weak forces, like a cosmic dust bunny. The visitor would be mostly vacuum with solid material making up only a small fraction of its total volume. Such extreme porosity could explain the visitor's low density and sensitivity to radiation pressure. A fluffy structure would respond strongly to subtle forces like sunlight pressure while remaining stable enough to survive interstellar travel. The dust bunny idea required formation processes that create extremely porous objects. Perhaps some star systems generate debris through mechanisms that produce fluffier material than the relatively compact objects common in our solar system. This hypothesis suggested that interstellar space might be populated by a previously unknown category of ultra-lightweight cosmic wanderers that challenge our assumptions about how matter behaves in the vacuum between stars. Gennady Borisov built his own telescope in his backyard in Crimea. This amateur astronomer spent countless nights scanning the sky for new comets. On August 30, 2019, he discovered something that would make astronomical history. Borisov noticed a fuzzy patch of light moving against the background stars. The object looked like a typical comet with a small glowing atmosphere around its nucleus. He reported his discovery to the Minor Planet Center, the organization that tracks new celestial objects. Amateur astronomers have discovered many comets throughout history. Building homemade telescopes and dedicating years to sky surveys, these enthusiasts often spot objects that professional facilities overlook. Most comet discoveries by amateurs turn out to be routine visitors from our solar system's outer regions. But Borisov's find was anything but routine. Follow-up observations revealed this fuzzy visitor was traveling on a path that would take it completely out of our solar system. The backyard astronomer had discovered only the second confirmed interstellar object in human history. Mathematical calculations revealed Borisov's comet was following an unmistakable interstellar trajectory. Unlike Oumuamua's puzzling path, this visitor's orbit left no room for doubt about its alien origins. Astronomers measure orbital eccentricity to determine whether objects belong to our solar system. Native residents have eccentricities less than 1.0, indicating closed elliptical orbits. Objects with eccentricities greater than 1.0 follow open hyperbolic paths that escape the Sun's gravity forever. Comet Borisov's orbital eccentricity measured approximately 3.4. This extreme value immediately identified the visitor as an interstellar wanderer. The mathematics were so clear that scientists confirmed its alien status within days of the initial discovery. This rapid confirmation contrasted sharply with Oumuamua's confusing trajectory. Borisov's comet followed a textbook example of an interstellar orbit, removing any uncertainty about its origins. The trajectory analysis provided unambiguous proof that objects from other star systems pass through our cosmic neighborhood more regularly than previously suspected. As Comet Borisov approached the Sun, it developed the classic features that define comets everywhere. A glowing atmosphere formed around its nucleus. A brilliant tail stretched behind it through space. This normal comet behavior contrasted dramatically with Oumuamua's mysterious inactivity. Borisov acted exactly like comets in our own solar system. Solar heating caused ices on its surface to sublimate directly from solid to gas, creating the characteristic coma and tail. The visitor's comet-like activity allowed astronomers to study it using well-established techniques. They could analyze the composition of gases streaming off its surface. They could measure the size and structure of its nucleus. They could track changes in brightness as the comet responded to solar heating. Borisov's typical comet behavior provided scientists with their first opportunity to study a normal interstellar object using familiar methods. The visitor proved that some cosmic wanderers from other star systems behave predictably, unlike the enigmatic Oumuamua that had puzzled astronomers with its unprecedented properties. Spectroscopic analysis of comet Borisov's emissions detected water vapor and carbon monoxide streaming off its surface. These molecular signatures provided the first direct chemical analysis of material from another star system. Spectroscopy works by analyzing how different molecules absorb and emit specific wavelengths of light. Each type of molecule creates a unique pattern of spectral lines, like a cosmic fingerprint. By studying these patterns, scientists can identify chemical composition without physically touching distant objects. The gases flowing from Borisov's nucleus showed remarkably familiar chemistry. Water and carbon monoxide are common in comets throughout our solar system. This similarity suggested that comet formation processes might be universal, creating similar materials around different stars. But subtle differences in the spectral signatures hinted at unique formation conditions. The relative amounts of different molecules varied slightly from typical solar system comets. These chemical fingerprints became humanity's first direct taste of matter forge in an alien star system, revealing both similarities and differences in cosmic chemistry across the galaxy. Scientists identified hydrogen cyanide and other complex molecules in Borisov's tail using sophisticated spectroscopic techniques. These detections revealed detailed information about the chemistry of materials from another planetary system. Hydrogen cyanide might sound dangerous, but it's actually common in comet chemistry. This molecule forms naturally in the cold, radiation-rich environment of outer planetary systems. Its presence in Borisov's emissions indicated familiar chemical processes operating around distant stars. The spectral analysis also detected traces of other molecules that form in typical comet ices. Ammonia, methanol, and various carbon compounds appeared in the visitor's chemical signature. Each detection provided clues about temperature and radiation conditions in Borisov's home system. This molecular inventory became humanity's first detailed recipe for an alien world's chemistry. The composition analysis revealed that basic chemical processes operate similarly throughout the galaxy, creating familiar building blocks of planetary systems around different stars. Borisov carried a sample of alien chemistry that proved surprisingly familiar to Earth-based scientists. Comet Borisov's nucleus measured approximately 1 kilometer in diameter. This relatively large size made it much easier to study than the tiny, enigmatic Oumuamua. Scientists determined the comet's size by analyzing how much sunlight its nucleus reflected combined with measurements of thermal emission in infrared wavelengths. Larger objects reflect more light and emit more heat, allowing researchers to calculate dimensions from brightness measurements. The kilometer-wide nucleus represented a substantial chunk of material from another star system. This size is typical for active comets in our own solar system, suggesting similar formation processes created planetary debris around different stars. Borisov's substantial size also explained why it remained active for so long during its passage through our solar system. Smaller comets can quickly exhaust their volatile ices when heated by the sun, but kilometer-sized nuclei contain enough frozen material to sustain gas and dust emissions for months or even years. The visitor's impressive dimensions allowed extended scientific observations that revealed unprecedented details about interstellar chemistry. Comet Borisov expelled relatively little dust compared to the amount of gas it released. This low dust-to-gas ratio suggested the visitor had preserved more primitive materials than typical comets in our solar system. The dust-to-gas ratio measures how much solid debris a comet releases compared to gaseous emissions. Most comets in our solar system have been altered by billions of years of thermal processing, radiation exposure, and occasional close approaches to the Sun. These processes tend to remove volatile gases while leaving behind dusty residues. Borisov's chemistry indicated less alteration than solar system comets typically experience. The visitor seemed to retain more of its original composition from when it first formed around its parent star. This pristine chemistry offered insights into unmodified materials from alien planetary formation. The low dust-to-gas ratio became a signature of interstellar preservation. Objects that spend millions of years drifting through the cold depths between stars might better maintain their original chemical composition than comets that remain gravitationally bound to active stellar systems. Borisov provided evidence that interstellar space serves as a cosmic deep freeze, preserving ancient chemistry from distant worlds. Comet Borisov began breaking apart as it rounded the Sun during its closest approach. Hubble Space Telescope images revealed the nucleus splitting into multiple fragments, exposing the visitor's internal structure. Comets are fragile objects held together by weak gravitational forces and frozen ices. When solar heating causes rapid sublimation of internal ices, the resulting gas pressure can overcome the structural integrity of the nucleus. The comet essentially explodes from the inside out. Borisov's fragmentation revealed important clues about its internal composition and structure. The way it broke apart suggested a loose aggregate of smaller pieces, rather than a solid monolithic body. This rubble pile structure is common among comets in our solar system. The breakup also exposed fresh internal material that had been protected from space weathering during the comet's interstellar journey. This allowed scientists to analyze truly pristine samples of alien chemistry that had remained frozen and unaltered for potentially millions of years. The visitor's structural weakness became a scientific opportunity, revealing interior materials that would otherwise have remained hidden. Astronomers traced Comet Borisov's trajectory backward through space to identify its likely stellar birthplace. The visitor's path pointed toward a region near the constellation Cassiopeia. By analyzing the comet's velocity and direction when it entered our solar system, scientists could calculate where it had been traveling through interstellar space. This process is like running a movie backward to see where an actor entered the scene. The trajectory analysis suggested Borisov had been wandering through space for several million years before encountering our solar system. During that time, it had traveled roughly 60 light-years from its point of origin. The stellar neighborhood near Cassiopeia contains several sun-like stars that could have hosted planetary systems capable of producing comets. While scientists couldn't identify the exact parent star, the trajectory analysis narrowed down the possible birthplaces to a specific region of our galactic neighborhood. This cosmic detective work provided the first clues about which stellar systems might be ejecting comets into interstellar space. Unlike Oumuamua's hasty passage, Comet Borisov remained visible for many months as it traveled through our solar system. This extended observation period allowed comprehensive scientific studies that had been impossible with the first interstellar visitor. Scientists detected Borisov while it was still approaching the Sun, giving them time to plan detailed observation campaigns. Major telescopes around the world and in space coordinated their efforts to maximize the scientific return from this rare opportunity. the comet remained bright enough for detailed spectroscopic analysis throughout its passage. This allowed scientists to track changes in its chemical composition and activity levels as solar heating varied. Such time series observations provided insights into how interstellar comets respond to stellar radiation. The extended visibility period also enabled multiple independent research teams to study the same object using different techniques. This redundancy improved confidence in the results and allowed cross-verification of measurements. Borisov's leisurely passage gave the astronomical community its first relaxed opportunity to study an interstellar visitor without racing against a rapidly fading target. Comet Borisov behaved exactly like a normal comet, making Oumuamua's bizarre properties even more mysterious by comparison. The second interstellar visitor provided a standard example of what interstellar objects should look like. Borisov developed typical comet features as it approached the Sun. Glowing coma, brilliant tail, gas emissions, and gradual brightening all matched expectations for how icy visitors should behave. This normal activity proved that interstellar comets could follow familiar patterns. The contrast with Oumuamua's unprecedented properties became stark when scientists compared the two interstellar visitors. One behaved exactly like expected, while the other defied every prediction about how objects should act when heated by the sun. Borisov's conventional behavior suggested that Oumuamua represented something truly unusual rather than typical interstellar material. The second visitor established a baseline for normal interstellar objects, highlighting just how extraordinary the first confirmed visitor had been. This comparison transformed Oumuamua from a puzzling anomaly into a genuinely mysterious object that challenges our understanding of what materials travel between the stars. Every object in space follows one of two fundamental path types: closed paths that loop forever, or open paths that escape forever. The mathematics behind these trajectories tells us immediately whether a visitor belongs to our solar system or comes from somewhere else. Scientists describe orbital shapes using a number called eccentricity. Think of eccentricity as a cosmic passport that reveals citizenship. Objects with eccentricity less than 1.0 follow closed elliptical orbits around the Sun. They're permanent residents of our solar system, but objects with eccentricity greater than 1.0 follow open hyperbolic paths. These visitors swoop in once and escape forever. No force can trap them in permanent orbits around our Sun. Interstellar objects like Oumuamua have eccentricities much greater than 1.0. This mathematical signature provides instant proof of alien origins. The hyperbolic trajectory becomes an unmistakable cosmic fingerprint that distinguishes true interstellar wanderers from solar system natives masquerading as visitors. How fast must an object move to escape our solar system forever? The answer reveals whether visitors originated here or traveled from interstellar space. Every location in our solar system has a specific escape velocity. This is the minimum speed needed to break free from the Sun's gravitational pull. Objects moving slower than escape velocity remain trapped in closed orbits. Objects moving faster escape to interstellar space. Interstellar visitors arrive with velocity exceeding our solar system's escape speed. This excess energy represents their cosmic kinetic inheritance from previous stellar encounters. The extra speed proves they've been wandering between stars long before discovering our neighborhood. Oumuamua possessed significant excess velocity when astronomers first detected it. This surplus energy above escape speed provided mathematical proof of the visitor's interstellar origins. The excess velocity became a cosmic odometer, recording the immense distances and gravitational encounters that shaped the wanderer's journey through space. Giant planets act like cosmic pinball bumpers for passing interstellar objects. These gravitational encounters can dramatically alter a visitor's speed and direction without any physical contact. When a small object passes close to a massive planet, the planet's gravity bends the visitor's trajectory. If the approach geometry aligns correctly, this gravitational slingshot can either accelerate or decelerate the passing object significantly. Jupiter and Saturn represent the most powerful gravitational scatterers in our solar system. Their enormous masses can deflect interstellar visitors by many degrees or change their speeds by several kilometers per second. These encounters reshape trajectories in ways that would require enormous rocket engines to achieve artificially. Gravitational scattering explains why some interstellar visitors might appear to follow unexpected paths through our solar system. The cosmic pinball effect can redirect wanderers toward inner planets or fling them back toward deep space along completely different trajectories. This gravitational reshuffling makes predicting visitor behavior much more complex than simple orbital mechanics would suggest. Every interstellar object experiences a single moment of maximum intensity during its passage through our solar system. This closest approach to the Sun represents the climax of the visitor's brief encounter with stellar radiation. Perihelion passage subjects cosmic wanderers to their highest temperatures and strongest gravitational accelerations. Solar heating can reach hundreds of degrees, potentially triggering gas emissions from icy surfaces. Tidal forces can stress fragile structures to their breaking points. The timing and distance of perihelion determine how much scientists can learn about each visitor. Objects that pass very close to the Sun heat up dramatically, potentially revealing hidden ices and internal composition. But extremely close approaches also limit observation time as visitors rapidly gain speed. Oumuamua's perihelion occurred at a distance of 23 million miles from the Sun. This moderately close approach provided sufficient heating to potentially trigger activity while remaining far enough for extended observations. The perihelion passage became the defining moment that shaped both the visitor's physical behavior and humanity's opportunity to study our first confirmed interstellar messenger. After interstellar visitors escape our solar system's gravitational influence, they return to traveling at their asymptotic velocity. This final speed determines where they'll wander next in the galaxy. Asymptotic velocity represents the speed an object maintains when it's far from any gravitational influences. For interstellar visitors, this final velocity depends on their original speed plus any changes caused by encounters with our Sun and planets. Most interstellar objects gain speed during their passage through our solar system. Gravitational acceleration during closest approach to the Sun typically increases their asymptotic velocity compared to their arrival speed. This cosmic boost sends visitors back into interstellar space moving faster than when they arrived. The asymptotic velocity determines which stellar neighborhoods visitors might encounter next. Objects moving at 26 kilometers per second will cross the distance between nearby stars in several million years. This final speed becomes the cosmic currency that determines future stellar encounters across the galaxy's vast distances. The direction from which interstellar visitors approach our solar system carries information about their previous travels through local stellar neighborhoods. This geometric signature provides clues about cosmic traffic patterns. Scientists measure incident angles relative to the ecliptic plane, the flat disk that contains Earth's orbit and most planets. Visitors arriving from high angles above or below this plane suggest origins from stellar systems with different orientations than our own. Most objects native to our solar system orbit within a few degrees of the ecliptic plane. But interstellar visitors can arrive from any direction, reflecting the three-dimensional nature of stellar positions throughout our galactic neighborhood. Oumuamua approached our solar system at a significant angle to the ecliptic plane. This steep incident angle provided additional confirmation of the visitor's interstellar origins while offering clues about which direction it had been traveling through local space. The arrival geometry became another piece of the cosmic puzzle, revealing the wanderer's previous journey between stars. How fast are interstellar visitors really moving? The answer depends on whether you measure their speed relative to our Sun or relative to the galaxy as a whole. Our Sun isn't stationary. It orbits the center of our galaxy at approximately 220 kilometers per second. This enormous orbital motion affects how we measure the velocities of interstellar visitors. Objects that seem fast relative to our Sun might be moving slowly through galactic space. Scientists must account for our Sun's galactic motion to determine visitors' true interstellar velocities. This correction reveals whether objects are keeping pace with local stellar motion or racing through space at unusually high speeds. The relative motion calculation helps identify which visitors represent typical interstellar debris versus high-velocity objects ejected by violent processes. Understanding these cosmic speed differences provides insights into the mechanisms that launch objects into interstellar space throughout our galactic neighborhood. Why do long-term predictions about interstellar visitor paths become unreliable? The gravitational influence of planets creates small changes that accumulate into large uncertainties over time. Every planet in our solar system tugs slightly on passing interstellar objects. These perturbations are individually small but collectively significant for long-term trajectory predictions. Each planetary encounter slightly modifies the visitor's path in ways that compound over time. The butterfly effect applies to orbital mechanics. Tiny changes in initial conditions can lead to dramatically different outcomes. Small errors in measuring a visitor's position or velocity translate into enormous uncertainties about where it will be years or decades later. Perturbation effects explain why scientists can accurately predict interstellar visitor positions for months or years but lose precision for longer time frames. The chaotic nature of multi-body gravitational interactions makes the solar system a fundamentally unpredictable environment for long-term orbital forecasting. How long do interstellar visitors remain in our solar system? The residence time depends on their speed and trajectory, but most cosmic wanderers stay for only months or a few years at most. Fast-moving visitors like Oumuamua race through our solar system in a matter of months. They approach from interstellar space, swing around the Sun, and escape back to deep space so quickly that scientists barely have time to organize observation campaigns. Slower visitors might linger for a year or two, allowing more extensive studies. But even these extended visits represent brief cosmic moments compared to the millions of years these objects spend traveling between stars. The limited residence time creates enormous pressure on the astronomical community to respond quickly to new discoveries. Every day of delay in organizing observations represents lost opportunities to study materials from alien star systems. This temporal constraint fundamentally shapes how scientists approach interstellar visitor research. How do scientists definitively distinguish between solar system natives and interstellar visitors? The mathematical relationship between orbital energy and angular momentum provides the ultimate test of cosmic citizenship. Orbital energy determines whether an object can escape our solar system's gravitational well. Negative energy indicates bound orbits that never escape. Positive energy indicates unbound trajectories that lead to interstellar space. Angular momentum measures how much rotational motion an object possesses around the Sun. Combined with orbital energy, angular momentum helps determine the exact shape and orientation of each visitor's path through space. The mathematical classification system creates clear boundaries between different types of cosmic objects. Solar system residents occupy specific regions of energy momentum space, while interstellar visitors cluster in completely different mathematical territories. This quantitative approach eliminates ambiguity about which objects truly originate from other star systems versus those that merely follow unusual orbits within our cosmic neighborhood. Interstellar visitors don't wait for scientists to catch up. From discovery to disappearance, researchers have only a brief window to extract decades' worth of information from these cosmic messengers. Most astronomical objects remain visible for years or even centuries. Stars shine steadily across human lifetimes. Planets maintain predictable positions that allow detailed study campaigns. Even asteroids and comets from our own solar system typically provide months or years of observation opportunities. But interstellar visitors race through our cosmic neighborhood on strict timetables. They brighten rapidly during approach, reach peak visibility for weeks, then fade beyond detection as they speed toward deep space. This compressed timeline forces scientists to choose between breadth and depth in their research priorities. Oumuamua exemplified this temporal challenge perfectly. Astronomers had roughly 4 months from discovery to final detection before the visitor faded beyond telescope capabilities. Every observation session represented irreplaceable opportunities to gather data that would never be available again. The vanishing act transforms interstellar visitor research into high-pressure scientific sprints, where time becomes more valuable than telescope access. Studying interstellar visitors is like trying to analyze a grain of sand from across a football field. These objects are simultaneously small, distant, and moving rapidly away from Earth. Brightness decreases with the square of distance, creating a mathematical nightmare for astronomers. An object that appears moderately bright at 50 million miles becomes 4 times dimmer at 100 million miles. As interstellar visitors race toward the outer solar system, they fade exponentially from view. Small size compounds the distance problem dramatically. Oumuamua measured only 200 meters long, roughly the size of 2 city blocks. At interstellar distances, such tiny objects reflect minuscule amounts of sunlight back toward Earth-based telescopes. The combination of small size, increasing distance, and rapid motion creates unprecedented observational challenges. Even the largest ground-based telescopes struggle to collect enough photons for meaningful measurements. This cosmic hide-and-seek game forces scientists to push their instruments to absolute sensitivity limits while racing against inevitable detection failure. Spectroscopy requires splitting faint starlight into component colors to reveal chemical fingerprints. But interstellar visitors often remain too dim for this rainbow analysis to work effectively. Spectrographs work by spreading light across many wavelength channels, similar to how prisms create rainbows. Each chemical element and molecule absorbs specific colors, creating dark lines in the spectrum that identify materials. This technique works brilliantly for bright objects, but struggles with faint targets. Splitting already dim light into hundreds of color channels makes each individual measurement extremely weak. The signal-to-noise ratio, the difference between real data and random background fluctuations, becomes so low that meaningful chemical identification becomes nearly impossible. Scientists must balance exposure time against object motion and fading. Longer exposures collect more photons but blur the spectrum as the visitor moves across the sky. Shorter exposures preserve sharpness but may not gather enough light for chemical analysis. This fundamental trade-off between signal strength and temporal resolution limits how much chemistry researchers can extract from rapidly departing cosmic messengers. Polarized light analysis can reveal surface texture and particle properties that other techniques miss. But measuring these subtle light twists requires extremely sensitive instruments and perfect observing conditions. Light waves oscillate in all directions as they travel through space. When light reflects off surfaces, it becomes partially polarized, meaning the waves align in preferred directions. Different surface materials and textures create characteristic polarization signatures. Polarimetry can distinguish between smooth rocky surfaces, fluffy dust aggregates, and icy compositions without requiring detailed spectroscopy. This technique provides information about particle sizes, surface roughness, and material properties that complement other analytical methods. But polarization measurements demand exceptional precision and stability from both instruments and atmospheric conditions. The polarization effects are typically only a few % of the total light, making them vulnerable to instrumental errors and atmospheric interference. For rapidly fading interstellar visitors, scientists often lack the luxury of waiting for perfect observing conditions to attempt these delicate measurements. Every object warmer than absolute zero glows with infrared heat radiation. Detecting this thermal emission from interstellar visitors reveals temperature, size, and thermal properties that visible light observations cannot provide. Thermal infrared observations work best when objects are relatively close to the sun and heated to temperatures that produce detectable heat radiation. The amount and wavelength distribution of thermal emission reveals information about surface materials, internal structure, and thermal conductivity. But interstellar visitors present unique thermal challenges. They approach from the cold depths of space, warm up briefly during closest approach to the sun, then cool rapidly as they retreat. This thermal evolution happens faster than most infrared observing campaigns can track effectively. Space-based infrared telescopes offer the best sensitivity for thermal measurements, but these facilities have limited observing time and often require months of advanced planning. The mismatch between thermal measurement requirements and rapid visitor timelines means scientists frequently miss optimal opportunities to study interstellar object temperatures and thermal behavior. Detecting gases escaping from interstellar visitor surfaces requires identifying individual molecules in near-perfect vacuum. This cosmic forensics work pushes gas detection technology to its absolute limits. Gas detection typically relies on spectroscopic identification of molecular emission or absorption lines. Each type of molecule, water vapor, carbon monoxide, hydrogen cyanide, produces characteristic spectral signatures that serve as molecular fingerprints. But interstellar visitors may release gases too sparse or chemically exotic for easy detection. Oumuamua showed no detectable gas emissions despite its mysterious acceleration. Either the visitor released invisible gases or used non-gas mechanisms for propulsion entirely. Ground-based telescopes must compete with Earth's atmospheric interference when detecting molecular signatures. Water vapor, carbon dioxide, and other atmospheric gases can mask or mimic emission lines from interstellar visitors. This atmospheric contamination makes definitive gas identification extremely challenging, especially for weak emission signatures from rapidly departing objects. Different isotopes of the same element act like atomic clocks that record the nuclear history of stellar neighborhoods. But measuring these subtle mass differences requires extraordinary spectroscopic precision. Isotopes are atoms with identical chemical properties, but different masses due to varying numbers of neutrons in their nuclei. The relative abundances of different isotopes preserve information about nuclear processes in the parent star system. For example, the ratio of oxygen-16 to oxygen-18 reveals information about stellar nucleosynthesis and supernova enrichment in the visitor's birthplace. Carbon isotope ratios provide clues about organic chemistry and thermal processing during formation. But isotope measurements demand spectroscopic resolution far exceeding normal chemical analysis requirements. The wavelength differences between isotopic lines are often smaller than typical instrument capabilities. For faint, rapidly moving interstellar visitors, achieving the necessary precision becomes nearly impossible with current technology. This analytical limitation means scientists often cannot access the nuclear archaeology that isotope ratios could provide about alien star system chemistry. Dust particles released by interstellar visitors carry information about surface composition and internal structure. But analyzing microscopic debris from millions of miles away requires indirect detection methods. When active interstellar visitors release dust, these particles scatter and absorb sunlight in ways that reveal their size distribution, composition, and optical properties. Different particle sizes create characteristic scattering patterns that telescopes can measure and analyze. Dust analysis also provides information about the mechanical properties of visitor surfaces. Fluffy, loosely bound surfaces produce different dust size distributions than compact, rocky materials. The dust release patterns can reveal internal layering and composition gradients. However, many interstellar visitors, like Oumuamua, show no detectable dust emissions whatsoever. This absence of dust signatures either indicates unusually clean, rocky surfaces or emission rates too low for telescopic detection. Without dust to analyze, scientists lose access to one of the most informative techniques for studying surface composition and structure remotely. Radar observations can measure surface roughness, electrical conductivity, and internal structure by bouncing radio waves off interstellar visitors. But these active measurements require objects to remain within radio telescope range. Radar works by transmitting powerful radio signals toward targets and analyzing the reflected echoes. Different surface materials and textures reflect radio waves with characteristic patterns that reveal physical and electrical properties invisible to optical telescopes. This technique can distinguish between metallic, rocky, and icy compositions. Radar can also penetrate surface layers to probe internal structure and detect buried composition changes. For objects with complex shapes, radar mapping can reveal three-dimensional structure with remarkable precision. But radar observations demand that interstellar visitors remain relatively close to Earth-based transmitting stations. The inverse fourth power law makes radar signals incredibly weak for distant targets. Transmitted power decreases with distance squared, and received echoes decrease with distance squared again. Most interstellar visitors move beyond effective radar range before scientists can organize comprehensive observation campaigns. With incomplete observational data, scientists can construct multiple plausible models that explain the same interstellar visitor behavior. This degeneracy problem makes definitive conclusions nearly impossible. Scientific modeling works best when researchers have abundant, high-quality data to constrain theoretical possibilities. Multiple independent measurements can eliminate incorrect models and converge on unique solutions that match observed behavior. But interstellar visitors provide sparse, noisy data collected under time pressure. A few brightness measurements, limited spectroscopic observations, and uncertain size estimates can support dramatically different compositional and structural models. For example, Oumuamua's mysterious acceleration could result from hydrogen ice sublimation, nitrogen ice outgassing, solar radiation pressure on a lightweight structure, or electromagnetic effects with charged surfaces. Each model fits the available data reasonably well, but they predict completely different material properties and formation histories. This modeling degeneracy forces scientists to acknowledge fundamental uncertainty about interstellar visitor properties despite intensive observational efforts. Interstellar visitors behave differently from anything in our solar system, eliminating familiar reference points for interpreting observations. Scientists must analyze completely unprecedented phenomena without reliable comparison standards. Most astronomical analysis relies on comparing new observations with well-studied reference objects. Asteroid researchers compare new discoveries with thousands of previously characterized rocky bodies. Comet scientists have centuries of observational data from solar system comets to guide interpretation. But interstellar visitors represent entirely new categories of objects with no local analogs. Their formation environments, compositions, and evolutionary histories differ fundamentally from solar system materials. Standard analytical techniques and interpretation frameworks may not apply to these alien wanderers. This absence of comparison standards forces scientists to develop new theoretical frameworks and analytical methods specifically for interstellar visitor research. Every measurement becomes an exercise in pioneering analysis rather than routine classification. The lack of reference points transforms interstellar visitor science into a field where every discovery challenges existing knowledge rather than confirming familiar patterns. Automated telescope systems scan vast areas of sky every night, capturing millions of images to detect anything that moves against the stellar background. These robotic observatories work continuously without human intervention, processing data faster than any astronomer could manage manually. Survey telescopes operate on a simple but powerful principle. They photograph the same regions of sky repeatedly over hours, days, or weeks. Computer algorithms then compare these images to identify objects that change position between observations. The Pan-STAR system that discovered Oumuamua represents this automated approach perfectly. 4 telescopes in Hawaii systematically photograph the entire visible sky every few nights. Each telescope captures images covering areas larger than the full moon in a single exposure. This repetitive imaging strategy catches objects that would be invisible to single observations. A faint dot that appears in one image but moves to a different position in the next image immediately flags as a potential discovery. The robotic eyes never get tired, never miss clear nights, and never overlook subtle movements that might indicate cosmic visitors approaching from interstellar space. Can computer algorithms instantly recognize interstellar visitors among thousands of routine asteroid discoveries? The mathematical challenge involves calculating orbital parameters quickly enough to identify cosmic wanderers before they fade from view. Traditional orbit determination requires multiple observations spread over several days or weeks to establish reliable trajectories. but interstellar visitors move so quickly that delays in classification can mean missing opportunities for detailed study entirely. Modern orbit discrimination algorithms use statistical methods to estimate trajectory types from minimal observational data. These systems can flag potentially hyperbolic orbits within hours of initial detection, even when orbital solutions remain uncertain. The mathematical race becomes critical for observation planning. Telescopes around the world need advance warning about which newly discovered objects might be interstellar visitors, requiring immediate priority attention. Fast orbit discrimination algorithms transform routine discovery notifications into urgent scientific alerts that mobilize global observational resources before cosmic messengers disappear forever. Artificial intelligence systems now learn to recognize interstellar object signatures by analyzing thousands of previous astronomical discoveries. These machine learning algorithms can identify potential cosmic visits faster than human astronomers reviewing data manually. Machine learning works by training computer systems on large datasets of known examples. Researchers feed algorithms thousands of orbit calculations, brightness measurements, and trajectory analysis from both solar system objects and confirmed interstellar visitors like Oumuamua and comet Borisov. The trained systems learn to recognize subtle patterns that distinguish interstellar visitors from solar system natives, unusual velocity vectors, specific brightness behaviors, and trajectory characteristics that human observers might overlook become automatic detection triggers for artificial intelligence. This automated pattern recognition dramatically increases the effective survey capacity of existing telescopes. Instead of human astronomers manually reviewing every discovery, machine learning systems can process thousands of detections per night and flag only the most promising interstellar visitor candidates. The artificial intelligence revolution multiplies humanity's cosmic visitor detection capabilities without requiring more telescopes or observing time. When survey telescopes discover potential interstellar visitors, automated systems immediately notify observatories worldwide through rapid communication networks. This instant alert system transforms individual discoveries into coordinated global observation campaigns. The alert process works through standardized communication protocols developed by the international astronomy community. Discovery notifications include precise coordinates, brightness estimates, and preliminary trajectory calculations that allow other telescopes to locate and track the new object immediately. Major observatories maintain rapid response capabilities specifically for interstellar visitor alerts. Pre-approved observation programs can interrupt scheduled research within hours to focus on newly discovered cosmic messengers. This coordinated response maximizes scientific return from brief observation windows. The Global Alert Network learned crucial lessons from Oumuamua's discovery, when valuable observation time was lost while astronomers realized the significance of their find. Modern alert systems ensure that potential interstellar visitors receive immediate attention from multiple facilities, preventing future missed opportunities to study these rare cosmic wanderers before they fade from detectability. The legacy survey of space and time will revolutionize interstellar object discovery when it begins operations. This massive telescope system promises to detect dozens of cosmic visitors annually instead of the current rate of one every few years. LSST combines an enormous mirror with advanced digital cameras to photograph the entire visible sky every few nights. The system will be roughly 100 times more sensitive than current survey telescopes, detecting much fainter objects at greater distances. This increased sensitivity will catch interstellar visitors much earlier in their approaches to our solar system, instead of discovering cosmic messengers after they've already passed closest approach to the Sun. LSST should detect them while they're still in the outer solar system, with months or years available for study. The expected discovery rate of several dozen interstellar visitors per year will transform this field from studying individual rare objects into statistical population science. Researchers will be able to characterize the typical properties, compositions, and origins of interstellar objects throughout our galactic neighborhood. LSST will turn interstellar visitor research from exotic case studies into systematic astronomical surveys. Networks designed to find potentially dangerous asteroids that might impact Earth routinely discover interstellar visitors as unintended bonus discoveries. These near-Earth object surveillance programs provide continuous sky monitoring that catches cosmic messengers by accident. NEO surveillance operates under the assumption that early warning about asteroid impacts could allow defensive measures. Multiple telescope systems scan the sky nightly, cataloging every moving object that might someday approach Earth's orbit dangerously close. These asteroid hunting programs have much broader sky coverage than specialized interstellar visitor searches. They monitor regions of space where Earth-threatening objects might appear, which happens to overlap significantly with the paths that interstellar visitors follow through our solar system. The side effect discovery potential means that asteroid defense investments indirectly support interstellar visitor research. Every upgrade to NEO surveillance capabilities increases the likelihood of detecting cosmic messengers from other star systems. This dual-purpose approach maximizes scientific return from planetary defense spending while advancing fundamental research about our galactic neighborhood. How many interstellar objects pass through our solar system undetected? Theoretical models combine galactic dynamics, stellar population statistics, and planetary formation theories to estimate the true population of cosmic wanderers. Statistical predictions begin with estimates of how many stars in our galaxy host planetary systems capable of ejecting debris into interstellar space. Current models suggest that most stars produce some interstellar objects during their planetary system formation and evolution phases. The models then calculate how these ejected objects distribute throughout galactic space and estimate encounter rates with our solar system. The mathematics must account for gravitational focusing effects, velocity distributions, and the three-dimensional structure of stellar motion in our local galactic neighborhood. Current theoretical models predict that several interstellar visitors per year should pass within detectable range of Earth-based telescopes. The fact that we've confirmed only 2 such objects suggests that either the models overestimate production rates or our detection capabilities remain insufficient to catch most cosmic visitors. These statistical predictions guide planning for next-generation survey systems and help scientists understand what fraction of interstellar traffic remains invisible. Future detection systems might catch interstellar visitors while they're still in the outer solar system, providing years of advance warning instead of discovering them during hasty departures. This early detection capability would revolutionize interstellar visitor research. Early detection requires much more sensitive telescopes capable of spotting extremely faint objects at vast distances. Visitors detected beyond the orbit of Jupiter or Saturn would remain observable for years as they approach and depart our solar system. Space-based telescopes offer the best prospects for early detection because they avoid atmospheric interference that limits ground-based sensitivity. Future space surveys could monitor the outer solar system continuously for incoming cosmic messengers. Extended observation periods would allow comprehensive studies impossible with current hasty detection scenarios. Scientists could track composition changes as visitors approach the Sun, monitor internal structure evolution during heating, and coordinate detailed observation campaigns months or years in advance. Early detection systems would transform interstellar visitor science from emergency response research into carefully planned investigation programs. Telescopes operating in space can detect infrared and ultraviolet radiation that Earth's atmosphere blocks completely. These orbital platforms provide unique capabilities for studying interstellar visitor compositions and thermal properties. Ground-based telescopes must work through miles of atmospheric interference that absorbs many wavelengths of light and creates turbulence that blurs images. Water vapor, carbon dioxide, and other atmospheric gases particularly interfere with infrared observations crucial for thermal studies. Space telescopes operate in perfect vacuum with no atmospheric limitations. They can observe across the entire electromagnetic spectrum and maintain perfect image stability without atmospheric turbulence. These advantages become especially important for faint, rapidly moving interstellar visitors. Future dedicated space missions for interstellar visitor research could provide continuous monitoring capabilities impossible from Earth's surface. Orbital platforms could track multiple visitors simultaneously, coordinate observations across different wavelengths, and maintain surveillance of the outer solar system for incoming cosmic messengers. Space-based detection represents the ultimate technological solution for comprehensive interstellar visitor research. Modern interstellar visitor research requires coordinating observations across the entire electromagnetic spectrum simultaneously. Radio telescopes, optical observatories, infrared satellites, and high-energy detectors must work together to capture complete pictures of cosmic visitors. Different wavelengths reveal different aspects of interstellar visitor properties. Radio observations can detect gas emissions invisible to optical telescopes. Infrared measurements reveal thermal properties and surface compositions. Ultraviolet and X-ray observations might detect exotic processes or unusual material interactions. International coordination networks allow astronomers to request simultaneous observations from facilities worldwide. When survey telescopes discover new interstellar visitors, alert systems can coordinate multi-wavelength observation campaigns within hours across different continents and space agencies. This comprehensive approach maximizes scientific return from each precious interstellar visitor discovery. Instead of studying cosmic messengers with single instruments or wavelength ranges, coordinated campaigns can characterize visitors across their entire emission spectra. Multi-wavelength cooperation transforms individual telescope discoveries into comprehensive astrophysical studies that reveal the full complexity of materials from other star systems. Professional astronomers can't possibly review all the data that modern survey telescopes generate every night. Citizen science programs recruit amateur astronomers and interested volunteers to help search through observational databases for overlooked interstellar visitors. Citizen science works by distributing image analysis tasks across thousands of volunteer participants. Online platforms allow anyone with internet access to examine telescope images, compare observations from different nights, and flag potentially interesting moving objects for professional follow-up. Amateur astronomers have already discovered numerous comets and asteroids using both personal telescopes and citizen science platforms. Their fresh perspectives and dedicated attention often catch subtle objects that automated detection algorithms miss. This human pattern recognition complements machine learning approaches. The discovery of comet Borisov by amateur astronomer Gennady Borisov demonstrates how individual dedication can make historic contributions to interstellar visitor research. Citizen science programs multiply this individual potential across thousands of participants worldwide, creating a distributed discovery network that supplements professional survey operations with volunteer enthusiasm and human intuition. Current asteroid and comet detection systems were designed primarily for solar system objects, creating blind spots that cause them to miss some types of interstellar visitors. Algorithm modifications can eliminate these detection biases. Traditional moving object detection assumes that discovered objects will follow bound orbits around the Sun. Algorithms optimize for detecting typical asteroid and comet trajectories while potentially overlooking the unusual velocity vectors that characterize interstellar visitors. Detection software also assumes certain brightness and color properties typical of solar system materials. Interstellar visitors with unusual compositions or surface properties might not match these built-in expectations, causing automated systems to ignore them as instrumental artifacts or contamination. Modern algorithm improvements specifically account for interstellar visitor characteristics in their detection criteria. Updated software can recognize hyperbolic trajectories, unusual color signatures, and brightness behaviors that would have been filtered out by earlier systems. These bias elimination efforts ensure that future survey operations will catch cosmic visitors regardless of how different they appear from familiar solar system objects. Engineers are building humanity's first spacecraft specifically designed to intercept interstellar visitors. The European Space Agency's Interceptor mission represents a revolutionary approach to studying cosmic wanderers up close instead of watching them from millions of miles away. Traditional space missions require years or decades of planning because scientists know exactly where their targets will be. But interstellar visitors appear unpredictably and depart quickly, making conventional mission planning impossible. The Interceptor spacecraft solves this problem by waiting in space at a strategic location where it can respond rapidly to newly discovered visitors. Think of it as a cosmic emergency room stationed at the gravitational equivalent of a major highway intersection. When astronomers discover the next interstellar visitor, mission controllers will redirect the waiting spacecraft to intercept the cosmic messenger. This approach could provide humanity's first close-up images and direct measurements of materials from another star system. The Interceptor design transforms interstellar visitor research from distant observation into hands-on space exploration. What if we could launch a spacecraft to any newly discovered interstellar visitor within weeks instead of waiting years for traditional mission development? Rapid response concepts envision keeping exploration vehicles ready for immediate deployment. Conventional spacecraft missions require extensive custom engineering for each specific target and trajectory. This process typically takes 5 to 10 years from initial planning to launch, but interstellar visitors don't provide that luxury of time for mission preparation. Rapid response missions would use standardized spacecraft designs that could be adapted quickly for different targets. Pre-built vehicles would remain in storage, ready for hasty modification and launch when astronomers discover promising interstellar visitors. The concept requires revolutionary changes in spacecraft design philosophy and launch operations. Instead of optimizing each mission for perfect efficiency, Rapid response systems would prioritize flexibility and speed over performance. This approach could transform interstellar visitor encounters from missed opportunities into routine scientific investigations. Solar radiation exerts gentle but continuous pressure that can accelerate spacecraft to incredible speeds over time. Solar sails use this free cosmic energy to chase interstellar visitors without carrying heavy rocket fuel. Solar sails work like cosmic windmills that capture momentum from sunlight instead of converting wind into electricity. Large, ultra-thin reflective surfaces collect solar radiation pressure and convert it into spacecraft acceleration. The acceleration is tiny but continuous, building up enormous velocities over months or years. This propulsion method provides unlimited fuel-free acceleration as long as sunlight remains available. Unlike chemical rockets that quickly exhaust their fuel, solar sails can accelerate continuously throughout entire interstellar pursuit missions. Solar sail technology could enable spacecraft to match the extreme velocities of departing interstellar visitors. A properly designed solar sail mission might catch up with Oumuamua even years after its discovery, despite the visitor's tremendous head start. This sailing technology opens possibilities for extended interstellar visitor studies that chemical propulsion cannot achieve. Imagine spacecraft smaller than smartphones accelerated by powerful laser beams to velocities approaching the speed of light. The breakthrough Starshot concept envisions fleets of tiny probes that could intercept interstellar visitors moving at any speed. These microprobes would weigh only grams, but carry miniaturized cameras, spectrometers, and communication systems. Ground-based laser arrays would accelerate the tiny spacecraft to 20% of light speed, fast enough to catch any interstellar visitor, regardless of how quickly it's departing our solar system. The extreme velocities create both opportunities and challenges. Microprobes could reach interstellar visitors within days or weeks of launch, but encounter speeds would be so high that detailed observations would last only seconds as the probes flash past their targets. This concept represents the ultimate extension of interstellar visitor research, transforming the field from passive observation to active high-speed interception. Breakthrough Starshot technology could provide close-up data from every future interstellar visitor, regardless of detection timing or departure velocity. Could future missions actually collect pieces of interstellar visitors and return them to Earth for analysis? This ultimate goal of interstellar visitor research would provide laboratory-quality data about materials from other star systems. Sample collection requires spacecraft to rendezvous with visitors rather than simply flying past them. The mission would need to match the visitor's velocity and trajectory precisely, then use specialized collection systems to gather dust, gas, or even solid fragments. The technical challenges are enormous. Interstellar visitors travel at velocities that make rendezvous extremely difficult. Most cosmic wanderers are also too small and fragile to support spacecraft landings. Collection methods would need to work in the vacuum of space while traveling at interstellar velocities. But the scientific payoff would be revolutionary. Earth-based laboratories could perform detailed chemical, mineralogical, and even biological analysis impossible with remote observations. Sample return missions could reveal the atomic-level composition of alien world materials and answer fundamental questions about planetary formation processes throughout the galaxy. Interstellar visitors serve as natural probes from other star systems, carrying direct evidence about planetary formation processes around different types of stars. This comparative approach revolutionizes our understanding of how planetary systems develop throughout the galaxy. Each interstellar visitor represents a sample from conditions that don't exist in our solar system. Different stellar masses, compositions, and environments create planetary formation processes that produce materials and structures unknown in our cosmic neighborhood. By studying multiple interstellar visitors from various stellar sources, scientists can begin to understand how planetary system formation varies with stellar properties. This comparative planetology approach reveals which aspects of our solar system are typical versus unique among galactic stellar families. The research transforms planetary science from a field limited to studying our single solar system example into a discipline that can characterize planetary formation processes throughout our region of the galaxy. Interstellar visitors become the key to understanding whether Earth-like worlds are common or rare among the billions of star systems in our cosmic neighborhood. Could life spread between star systems by hitchhiking on interstellar visitors? The panspermia hypothesis suggests that hardy microorganisms might survive the journey through deep space, potentially seeding life throughout the galaxy. Panspermia requires that some form of life can survive the extreme conditions of interstellar space. Microorganisms would need to endure cosmic radiation near absolute zero temperatures and millions of years of travel between stellar systems. Some Earth organisms demonstrate remarkable survival abilities under extreme conditions. Tardigrades can survive space vacuum, radiation, and temperature extremes that would kill most life forms. If similar hardy organisms exist elsewhere, they might potentially survive interstellar journeys. Detailed analysis of interstellar visitor materials could test the panspermia hypothesis directly, finding organic molecules, fossilized microorganisms, or even active biological material on cosmic wanderers would revolutionize our understanding of life's distribution throughout the galaxy. These visitors might carry the ultimate answer to whether life on Earth represents a unique cosmic accident or part of a galaxy-wide biological network. How typical is our solar system compared to the thousands of other planetary systems astronomers have discovered? Interstellar visitors provide direct samples for comparison with our local cosmic neighborhood. For decades, scientists could only study planetary formation by examining objects within our own solar system. This limited perspective made it impossible to determine which features represent universal planetary formation processes versus unique local conditions. Interstellar visitors break this observational limitation by bringing materials formed under completely different stellar conditions. Each cosmic wanderer carries chemical and physical signatures that reveal formation processes around other types of stars. These comparative studies are already revealing surprising results. Some interstellar visitors show compositions similar to solar system materials, suggesting universal chemical processes. Others display exotic properties that challenge existing theories about planetary formation. This comparison approach transforms our solar system from humanity's only example of planetary development into one data point in a much larger galactic survey. Interstellar visitors from different stellar sources carry chemical fingerprints that reveal the history of element production and distribution throughout our region of the galaxy. This cosmic archaeology provides insights into how the galaxy's chemical composition has evolved over billions of years. Different types of stars produce different elements through nuclear fusion and explosive events. Massive stars create heavy elements like iron and nickel. Smaller stars contribute lighter elements like carbon and oxygen. Supernovas distribute these elements throughout galactic space. The chemical composition of interstellar visitors reflects the element production history of their birthplace stellar neighborhoods. By analyzing materials from cosmic wanderers that originated around different types of stars, scientists can map chemical evolution patterns across the galaxy. This galactic chemistry survey reveals how stellar populations have influenced the distribution of elements available for planetary formation in different regions of space. The research helps explain why some stellar neighborhoods might be better suited for producing Earth-like worlds than others, based on the availability of essential elements for rocky planet formation and potentially life. Interstellar visitor research is evolving into an entirely new branch of astronomy with its own specialized techniques, theoretical frameworks, and research questions. This emerging field bridges planetary science, galactic astronomy, and astrobiology. The discipline requires unique analytical methods that combine rapid response observational techniques with theoretical models of interstellar transport processes. Scientists must understand both planetary formation mechanisms and galactic dynamics to interpret interstellar visitor properties correctly. Future interstellar science programs will likely include dedicated space missions, specialized detection networks, and international cooperation agreements for sharing observation time and data. Universities may begin offering courses specifically focused on interstellar visitor research methods and theories. The field also opens possibilities for detecting evidence of technological civilizations if any interstellar visitors turn out to be artificial rather than natural. While most cosmic wanderers will likely be natural planetary debris, the statistical possibility of encountering technological artifacts cannot be completely eliminated. Interstellar visitor science may become humanity's first systematic search for physical evidence of other technological civilizations in our galactic neighborhood.